Welcome to video 2. All right, so of crystalline solids, they can be broken up into 4 main groups. Group 1 that we haven't talked about at all, but is something called metallic elements. We have ionic. We have a group we're going to call molecular, and last but not least, there's a group that we're going to call a network solid. And what differentiates these three is the nature of the intermolecular forces that are holding them together. Now, I want to stress this is the intermolecular or interparticle forces. For example, I'm using ice as an example for the molecular compounds. I'm talking about the dipole-dipole interactions and the hydrogen bonds that attract one water molecule to another. I am not talking about the bonds that hold a hydrogen atom to a particular oxygen atom. So let's always keep that in mind. These are intermolecular interactions. Now, that being said, keep that in mind because this can get a little hard to keep track of. Because we're actually going to be talking about 3 types of intermolecular interactions you haven't heard about before. And the molecular are the ones that you do know. So I'm going to talk about these one at a time. And I'm going to start with the ionic ones because that's actually the one that is the most, I think, easy to understand. So ionic compounds. As the name might lead you to believe, these are compounds that consist of ions. And what holds them together, here I'm talking about what attracts, let's say this chloride ion to these neighboring 4 sodium ions. And quite frankly, the repulsion for these other chloride ions that are slightly further away are strictly Coulombic interactions. It's just because these particles have an explicit charge on them. So we call this ion-ion interactions or ion-ion forces. Now, because there are a large number of repulsive interactions to consider, so again, let's look at this chloride ion right here. Its nearest neighbors, so these two are all ions of the opposite charge, which is good. And the closer they are to ions of the opposite charge, the stronger the interaction is, the better it is. But not much further away, you have 4 other chloride ions. These are going to be repulsive interactions, but they are a little bit further away. So these 4 attractions are stronger than these 4 repulsions. So the attractions are going to kind of win. And you can actually keep playing this game for any ion that you would pick in the structure and however far you want it to go out. Because this is arranged in a very specific manner, that you will always have more attractive interactions than repulsive interactions. And because of that, and how important this spacing or this placing is, that these things adopt a very regular and very precise lattice structure. And that's the only way that the attractions can be made to outweigh the repulsions. Some physical properties that these guys have. So relatively speaking, these are very large intermolecular forces. These are at least 10 to 100 times as strong as the London dispersion, dipole-dipole interactions, and the hydrogen bonding that we've talked about previously. Now, because of this, these have extremely high melting points. We're talking about hundreds, if not thousands of degrees Celsius. The solids are poor conductors of heat and of electricity. So let's talk about this. For something to be a conductor of electricity, you have to have 2 requirements that need to be met. One is that you have to have some sort of charge carrier, some sort of charged particle, and it has to be mobile. Now, this is chock full of charged particles. It's an ionic compound, but because they are each charged particle is locked into place in this lattice, and they can only move back and forth in between just a little bit in their assigned place. They can't move like from here to here or something like that, or from there to there. So they're not mobile charge carriers. So they don't conduct electricity very well. It's a little bit beyond the pay grade of this class, but typically heat conduction works in a very similar manner. So in almost all cases, if something is a poor conductor of electricity, it is also going to be a poor conductor of heat. Now, once you melt these things, you are not confined to this very rigid lattice structure. The ions can move around each other. So liquid ionic compounds are actually very good conductors of heat and of electricity, but you have to work pretty hard to actually, heat them hot enough to melt. And the other thing is that they are brittle. What does brittle mean? That means if you were to hit this piece of table salt, you get a whole bunch of smaller pieces of table salt, that shatters when you hit them or something like that. All right, so those are the high points of ionic compounds. Molecular compounds, on the other hand, are the next step we're going to talk about. And these are compounds that exhibit the intermolecular forces that we've actually been talking about. So this includes most substances that have covalent bonds, and also most elements that are not metals. But again, but generally things that are held together by covalent bonds. So these solids, like in our figure here, are held together by intermolecular forces that exist between the molecules, like the dotted lines here. And in this case, they are numerous. So these can be any one or combination of London dispersion interactions, dipole-dipole interactions, and hydrogen bonds. In the case of water, you've got all three. So what are the properties, what are the macroscopic properties of these solids? Compared to the ion-ion interactions, these are relatively weak. So these bonds are worth about maybe 0.1 to, let's say, 5 or 10 kilojoules per mole, as opposed to a few hundred or a few thousand in ionic compounds. Because these intermolecular forces are relatively weak, they have relatively low melting points. And because you don't have mobile charge carriers, now in the case, most of these are neutral compounds or covalent compounds, so they aren't made of ions. So there are really no charged particles to try to move around anywhere. So these are generally not good conductors of heat and electricity. And that's pretty it for the molecular type compounds. All right, one of the new ones, this thing called a metallic solid. All right, as the name might imply, this applies to metallic elements, metals, and also alloys, which are just mixtures or solutions, if you will, of metals. They just happen to be solutions that are in the solid phase. Now, again, this is way beyond the pay grade for this class, but just to really sum it up, the way that metallic elements are held together is actually quite different, in that there's at least some number of electrons that are able to move across the entire piece of metal. One of the names for this is something that is called the electron sea, or the electron cloud model. And it's just saying that, for each atom, there might be 1 to 2 to 3 electrons that it contributes to just basically one huge bond that covers the entire sample. So this is, again, an orbital that an orbital or an electron state that covers the entire solid. And this is sort of like having every atom explicitly bonded to every other atom. So electrons are shared completely among all atoms in there. This results in a ridiculously strong intermolecular force. It's on the order of the ionic compounds, if not a little bit stronger. Now this results in exceptionally high boiling and melting points for these compounds. And this is partly because we haven't talked about boiling points, but this interaction is actually present in the liquid phase as well as in the solid. So metallic elements have normally most compounds have a relatively small liquid range. Metallic elements actually have a fairly large one. Now, because you've got all these electrons that can go here and there everywhere throughout the entire solid of stuff, this is why metals are very good conductors of heat and of electricity. I mean, the charged particles here are just electrons. And they are malleable. If you have not heard that word before, yeah, it's quite possible. Malleable is the opposite of brittle. So what that means, and I will show you on the next slide. So if something is brittle, you hit it with a hammer and it breaks up into smaller pieces. If something is malleable, if you hit it with a hammer, you still have one piece of the stuff. It is just now a little bit flatter. Now this figure is also useful to demonstrate two of the big differences between ionic and metallic compounds and why one is malleable and one is brittle. And it involves looking at the molecular structure for here. So this is a simplified two-dimensional ionic structure, but I think it hits the point that if you want to maximize the attractive interactions and minimize the repulsive interactions, you kind of want them alternating. So in this one, if you look at any one particular ion, let's look at this positive ion right here, its nearest neighbors are all ions of the opposite charge, which is good. And the ions of the like charge are always just a little bit further away, so the attractions will win out over the repulsions. And for a two-dimensional grid, this is actually the best you can do. This is the best way to arrange them if you want to maximize the attractions and minimize the repulsions. Now think about what is the difference between the best possible arrangement and the worst possible arrangement. It is 1 atomic diameter. If you were to shift this group of 8 ions down by 1, what happens? Now at that point, every interaction is repulsive. Everything is right next to something of the same charge. So that is an incredible amount of electrostatic repulsion, and they blow apart. And so this is exactly what's happening on a molecular scale when you hit this with a hammer. That you're shifting things, and as soon as these things line up like this, the repulsion is enough to physically break it up into many, many pieces. There are some compounds for which, if you have a steady hand, a very thin enough chisel, you can cleave some of these ionic compounds to a point where they are atomically flat over several square inches. It's kind of neat to see. Why don't metals do this? It's because of this whole electron cloud thing that they've got going. So in this case, the attractive interactions don't matter so much about where the nuclei explicitly are, because you've got a bunch of very fast, very free-roaming electrons that they themselves can move around instantaneously to adjust for any new repulsions that the nuclei can adopt. So one of the differences here is that, yeah, these are all positive charges, but what this little yellow background is explaining that you've got a whole bunch of fuzzy electron density in between them. And in that case, the attractive interactions end up winning. So you hit this with a hammer, you knock down, you shift down a few rows of these things, but it doesn't really matter because the electrons can instantaneously, or just about instantaneously, shift around to readjust, balance everything back out, and not have the whole thing blow apart, just be a little bit flatter. And again, this interaction is even existent in the liquid phase as well, which is not the case for some of the other ones. All right, so that's number 3. Which is why they have an extended extent, which is why, as I said before, the metallic elements or the metallic solids have a pretty large liquid phase. So the next kind, which is the fourth kind of solid, is also a new one that is called a network solid. And this is the one that can be a little bit confusing because in network solid, the most common example of which is probably diamond, that the covalent bond is what the actual intermolecular or interparticle force is. So basically, the entire chunk of stuff is one large molecule, one big covalent molecule that could be, the size of a visible diamond piece. So what does this diamond in particular look like? It is it's pure carbon, and it is a bunch of carbon atoms, each of which that is covalently bound to 4 nearest neighbors. And that carbon is bound to 4 other neighbors. So it's 4. So they're all tetrahedrally arranged around each other. And there's covalent bonds attaching any one atom to all of the other atoms. So it's one big molecule. Now these are also, they're quite rare. There aren't a whole lot of examples of them. Diamond is one of them. Quartz, silicon dioxide, and silicon carbide are probably the other most common forms of this. Now, because the intermolecular forces in this type of solid are actual straight up covalent bonds, these are very, very, very strong, which makes these incredibly hard substances, diamond being in fact the hardest known substance. And because these things don't have mobile electrons, so in this case, the electrons that are shared are pretty much just shared between adjacent or neighboring carbon atoms and not throughout the entire molecule like in the metallic solids. So these are very hard substances, but they tend to be fairly poor conductors of heat and of electricity. Again, fairly rare. I do want to point out one other type of network solid, because it's technically network solid, and that's graphite. So graphite is also pure carbon, but and it's actually more stable than the diamond form. But it's very interesting that it is a network solid in 2 directions and a molecular solid in the 3rd. So here is, what this looks like. What the graphite structure is it is a whole bunch of very flat sheets of 6-membered rings of carbon. So if you were looking at them from the top, you would see this. Again, it's just a bunch of interlocking carbon atoms that form hexagons. So each little intersection here is a carbon atom. And it turns out that these rings are perfectly flat. So these sheets of interlocked rings are also perfectly flat. They're covalently bound to each other. So like in this direction, going like left to right and front and back, it is a network solid. These sheets, these flat sheets, are laid on top of each other. And there is no bonding, there's no covalent bonding in between the sheets. The sheets are held together only by London dispersion interactions. So this is an interesting case where you've got something that is a network solid in 2 dimensions, in this case left and right, back and forth, and is a molecular solid up and down. And it's fairly easy to slide, for these sheets to slide on top or slide away from each other, which is why it's a good thing to write with. So the sheets, so when you are writing on your paper in a pencil, these sheets are shearing off the outer layer of this. Right. This is also why the reason for some of the more unique properties of graphite, that it actually does conduct electricity reasonably well, because with this arrangement, as opposed to the tetrahedral arrangement, there actually are electrons that go back and forth throughout these entire sheets quite nicely. They don't jump from sheet to sheet, but they can still go from any one corner of the sheet to the other corner of the sheet. So in case you're wondering why If you get, there are some cases where graphite components are actually quite strong. Not like pencil leads, and you might think that if something can shear away from itself as easily as this, that would actually not be a good thing to make, I don't know, a bike frame or an auto frame out of. And the key to that is what you have to do is take a bunch of these sheets of graphite and make sure that you've got that these sheets are not just all stacked up on top of each other, that they are going in all directions. Sort of like when you lay bricks, you don't lay them up and you actually stagger the rows. And if you do this with these graphite sheets, you can end up with some, within a sheet, the bonding is incredibly strong. If you construct the material right, you can arrange it so that there's never a very large gap. There's never a very large sheet like this, that these sheets are going in all sorts of directions, so you're not particularly weak in any direction. So this is kind of a unique compound. Remember that it is actually the more stable form of graphite. And again, a quick summary. Metallic solids, what the fundamental particle, what the type of solid is, what the fundamental particles are, and this is sort of a basic, and some examples. And I will not read them because, well, you can do that. So I will see you at the very last video.